4.4.
Thomas's exponential and logarithmic functions. All right, let's head through this. No graphs. It's all playing with numbers, playing with logs and exponentials. Number one, we've got 2 to the x minus 4 equals 2 to the 5th power. They're both the same base. When the bases match, the exponents match. We've looked at that a few times. So set the exponents equal to each other, move the 4 over, and you've got x equals 9. And if you put that 9 in there, 9 minus 4 is 5. 2 to the 5th equals 2 to the 5th. Makes some good sense. This is B here. We got 5 to the 3x minus 1 equals 125. We need those to be the same base. You know that 5 and 125 are related to each other. This is 5 times 5 times 5. This is 5 to the 3rd power. So we want to look at a lower base for this one. We'll relate both of them back to the base of 5. So 125 is 5 to the 3rd power. Bases match. Exponents can be set equal to each other. So we're solving for x. Add 1 to both sides. Divide by 3. We get x equals 4/3, and that's our answer. If we plug in 4/3, the 3 on top with the 3 on bottom will cancel, and we've got 4 minus 1, which is a 3. 5 to the 3rd equals 125. C is 8 to the x plus 3 equals 4 to the 5 minus 2x. Those are going to have to be converted to the same base also. 4 is the smaller one, but 4 squared is 16, not 8. And we need these two guys to be based off the same base. So let's jack them both down to 2's. So 8 is 2 times 2 times 2. 8 is 2 to the 3rd. So we'll rewrite 8 as 2 to the 3rd. And then it'll be multiplied times the exponent that's already sitting there. So that exponent of 3 gets to multiply times the pre-existing exponent. Same thing over here. 4 is 2 squared, and that exponent that we put up there will now be multiplied times the exponent that was already in place. Now the bases match, so the exponents can be set equal to each other. I'm going to multiply, distribute there. We get 3x plus 9 equals 10 minus 4x. I'm going to move stuff around. I'm going to move the 4x over. Move the 9 over. Divide by 7. So there we get our answer. X is 1/7. And D, we've got 1/4 equals 8 to the x power. Again, we're going to have to convert that 8 and that 4 into 2's. So we'll bring both of these down to a power of 2. So this will be 2 squared. 8 will be 2 to the 3rd power, and then multiply times that x that's already up there in the exponent position. We still don't have matching bases because what we've got is a 2 in the denominator. This is a 2 in the numerator. So let's kick this guy up to the top. If we kick him up to the top, his exponent is a 2. It now needs to be a -2 because we moved him. So he gains a negative on the way up. Now we've got bases match, so the exponents match. Divide by 3, and you get x equals -2/3. And if you were to put that -2/3 right there, the negative would make it 1/8. We'd take the cube root of that, that's a 2, and we'd square it. So we'd get 1/4 equals 1/4. Works out. Let's look at number 2A. Let me see if Thomas has given you some interesting instructions here. I don't want to lose his instructions. Solve each equation. Round your answer to the nearest hundredth. Do not round any intermediate computations, meaning leave the number in your calculator, grab it, and then complete the calculations. Don't round until the very last step of what you're doing. So let's see what we got here. We've got log of 2 to the x power equals log of base 10, because it's a common logarithm, log of 7. Common logarithm of 2 to the x power equals a common logarithm of 7. So first thing you want to do, we're trying to get x by itself. We want to get this x by itself. Let's use the power property to send it to the front. X times the log, common log of 2 equals the common log of 7. We're still trying to get x by itself. This says times the log of 2. In order to get x by itself, this is multiplied. You want to divide by the common log of 2. There, got that happening. And now if we've done it to one side, we have to do it to both sides. So we're going to divide by the common log of 2 on both sides. So we're going to get x equals the common log of 7 over the common log of 2. Grab your calculator, almost done here. Log of 7, close it out, divided by log of 2, and we're getting 2.07354922. That's good. What we want to do here is round to the nearest hundredth, I think he said. Yes, he did. So make it look like money. So $2.81. That 7 will make the 0 go back up to a 1. If you want to check it, you don't need to, but common log of 2 raised to the 2.81. So we're taking the common log of 2 raised to the 2.81, and that should give you that number. Remember that, 0.846, something like that. And the common log of 7 is 0.845. We did some rounding here, so that's why there's a tiny discrepancy in those two numbers, but they will match. Let's look at B. We're doing 10 to the x equals 8,000. Okay, this is an exponential because it's got a variable in the exponent spot. We looked at that in 4.1 first thing, I think. What we want to do here is, we're not going to be able to move this x to the front yet because it doesn't have the word log in front of it. We're not taking the log. But what you're allowed to do is take the log of both sides, and then we can make it look like a. So let's take the log of 10 to the x power and take the log of 8,000. So now that's legal. Now what we want to do is fling this x in front like we did in the previous problem. X times the log of 10 equals the log of 8,000. And then we're going to do the exact same thing we did in the previous problem. You want to get x by itself, so you want to divide by the common log of 10. So divide here by the common log of 10. Whatever you do on one side, you need to do on both sides. You can proceed here, or you can take a second and think, and you could have thought a second over here too. You know that the base is a 10. What do you need to raise 10 to? What exponent will raise 10 to a 10? Well, that's a 1. So the answer in the bottom here is a 1. That's a 1. Up here, it was a 1. So we didn't really need to divide by it if you recognized it was a 1 right there. So either way, we're finally down to x equals the common log of 8,000. Grab your calculator. Common log of 8,000 equals 3.90, rounding to the nearest hundredth, make it look like money. And sure enough, if you put that in there, 10, I'm going to use the key up here, 10, got to hit the secondary button, 10 raised to the 3.9 will give you 7,943, and that's very close to 8,000. Remember, we rounded this number pretty judiciously. So 7,943 is awfully close to 8,000. If you had kept this, if I'd kept this in the calculator a little bit better, and we put it in here, we'd be great. Let's see, let's look at C. C has got 3 to the negative 0.02x equals 0.07. Same game as the previous two problems. we want to end up with a logarithmic problem so we can sling this in front and divide by the log. So slap a log on both of these. Negative 0.02x equals the log of 0.07. What are we doing in terms of space there? I'll go ahead and scoot it down. Good deal. So we've got them both in logarithmic form. Now we can sling this exponent out to the front. Negative 0.02x times log of 3 equals log of 0.07. You want to get x by itself. So we've got this guy times x times a log. We're able to divide by the log first and get out of the log business. Divide there. The logs go away there. We want to divide both sides by a common log of 3. So we get a negative 0.02x equals, grab your calculator. We're doing log of 0.07, close that parentheses out, divided by log of 3, and that equals negative 2.42. Just checking my notes to make sure we're keeping up. Equals negative 2.4205, blah, blah, blah. Keep that in your calculator. That's the intermediate rounding. We don't want to do that. Now divide by negative 0.02 to get x all by itself. So x equals, take what's in your calculator and divide it by negative 0.02. Hit that equals button, and you're getting 121 and 3 cents if you were rounding it off to nearest hundredth. 121.03. If you were to plug that back in here, 3 to that number, negative 0.02, times 121, you'd get about 0.07. It checks. All right, next, let's look at D in this series of problems. 4 plus 3e raised to the 2x equals 11. We're trying to get x by itself. We want to find out what x is, so we need to get closer and closer to x. This is our first time to have a number attached by plus or minus. Send him over to the other side. Okay, now this looks very much like the previous problem, but in our process of doing this, let's see what we want to do here. Yeah, let's go ahead and divide, get closer. Let's divide by 3. There are a couple of different ways you can do this, and this makes just as much sense as anything else. Now let's slap logs on both sides, except don't use log because we've got an e here. That's the hint that you want to use natural log for this problem. So let's slap natural log of e to the 2x equals natural log of 7/3. Okay. You can either now or later recognize that this is an understood base e. E raised to what exponent will give you e to the 2x. So this side is going to become 2x. Let me write that over here. Let's see. This is, remember there's an understood e there, and then the answer is always an x. Do the circly thing. So e to what will give you e to the 2x? E to the unknown will give you that. So this piece right here is just 2x. 2x equals the natural log of 7/3. Let's go ahead and get a value for that. 2 times x equals natural log of 7 ABC3 equals, and we're getting a 0.847 and some change. Leave that in your calculator. Divide by 2. And we're getting x equals 0.42, ooh, barely. Nope, not barely. We're getting 0.4236. Good answer there. To the nearest hundredth, so 0.42 is what he's looking for. 0.42 there. All right, next page. Number 3. It says warning up there. Always check your answers. Do not always check that your answers do not make a zero or negative inside the logarithm. I'll show you what we're talking about there when we get there. And then what he talks about here is that if the logs match, log base b, log base b, log base b of x, log base b of y, then x equals y. Very much like when we had same bases, so the exponents matched. Okay, let's grab onto some of these. Let's look at 3a. The problem looks like log base 2 of 5x minus 1 equals log base 2 of 2x plus 17. Again, if both of them are in log base 2, or log base matching, and these are both in log base 2, then their logs match. 5x minus 1 equals 2x plus 17. Let's move this around. You can handle this all day long. Add 1. 3x equals 18, so x equals 6. What we want to do is we've got to plug it back into the parentheses to make sure we don't end up with a negative here or a negative there, or a 0. 0 or negative are against the rules. So 6, 5 times 6 is 30. That gives us 29 there. That's good. You can ask yourself, what can you raise 2 up to make it be a 29? That's a legal question. 2 times 12 is 2 times 6 is 12. 12 plus 17 is 29. Again, that's not a 0 or a negative number, so we're good. So this is a good answer. Let's look at B. We've got common log of x minus 7 equals common log of 5 minus x. They're both log base 10 or just common logs. So we can say x minus 7 equals 5 minus x. Let's add x to both sides. 2x minus 7 equals 5. Move the 7 over. And we get 2x equals 12, x equals 6. Seems to be a common answer going around here. Can you still see that? Yeah, you can. Good. Let's plug it in. 6 minus 7 gives you a negative 1. That's a problem. Same thing over here. 5 minus 6 gives you a negative 1. So it kind of looks like it works. Common log of negative 1, common log of negative 1. But that's saying log base 10 of negative 1 equals x. It's saying 10 to what power will give you a negative 1. You can never raise 10 to any power that will give you a negative answer. So this is just not an answer. There is no answer. No answer possible on 3B. You can't tell because this looks like 6, looks like a perfectly good number. But if you plug it in, 6 minus 7 gives you a negative answer. Negative, taking a log of a negative number. Not legal. Okay. Let's move on to the Are You Readies. It says solve each of the following equations which contain a variable in the denominator. So on the first Are You Ready, we've got 5 over x minus 3 equals 2. The thing we've got to be careful of is that we don't end up with an answer that will zero out this denominator. So we've got to be careful that we don't get x equals 3 as an answer, because 3 minus 3, kablooey. What you want to do is put this guy over 1. Then we're able to cross multiply. So 2 times x minus 3 equals 5 times 1. And it doesn't matter if you've put your 2 times x minus 3 on that side and your 5 times 1 on the other side. Doesn't matter. 2x minus 6 equals 5. Add 6. 2x equals 11. So x equals 11 over 2. 11 over 2 is not 3, so it's perfectly good. We're in good shape. That's the answer. Let's look at B in the Are You Readies. We have got 3x minus 7 over 2x plus 4 equals 5. Again, we have to be sure that the denominator does not become 0. So let's set it equal to 0 and see what our problem would be. Move the 4 over and divide by 2. So x cannot be negative 2. We got to make sure that x does not become negative 2. If it does, we don't have an answer. Let's keep moving. What we're going to do to solve for this is put this guy over 1 and cross multiply. So I'm going to put 5 times 2x plus 4 equals 1 times 3x minus 7. 10x plus 20 equals 3x minus 7. Move the 3x to the other side to join the 10x. Move the 20 over. And 7x equals negative 27. Divide by 7, and there's our answer. We get an answer of x equals negative 27 over 7. And it was not a negative 2, so we're good. And that's a good answer. Okay, so that is preparing for you for what you'll see right now. Let's look at 4a. 4a says solve each equation. So we've got log of 3x minus 4 minus log of x plus 1 equals log of 2. So up in the earlier problems, when we had both logs and we set these pieces equal to each other, we had one log and one log. We had one log and one log, so we could grab their little their terms. Natural log and natural log, so we could grab their terms, although that one's not exactly what we were doing. This is different from that. This has got a pair of logs on this side of the equal sign and only one there. That's not as flexible. We're not going to be able to do that. So what we are going to need to do is use the property from the previous section that had us dividing when we had a subtraction problem. So this becomes the log of 3x minus 4 over x plus 1 equals the common log of 2. So now we've got a common log equal to a common log, and we're able to set these two pieces equal to each other. So 3x minus 4 over x plus 1 equals 2. That's why we did the previous two Are You Readies, so that now you know to solve for x, put that over 1 and do some cross multiplying. So we get 3x minus 4 times 1 equals 2 times x plus 1. So 3x minus 4 equals 2x plus 2. Move the 2x over. X minus 4 equals 2. Add the 4. X equals 6. Let's just make sure we're going to be okay. We've got 18 minus 4. 3 times 6 is 18. 18 minus 4 will give us a 14 for the numerator. 6 plus 1 is a 7. 14 over 7 is 2. So this is the the common log of 2 equals the common log of 2. And that works. Nobody was a negative number in either that log or that log, so we're okay. 4b, we've got the natural log of x plus 3 plus the natural log of x equals the natural log of 10. Same kind of problem as the previous problem. We have too many natural logs. We're going to have to combine these two. You know what, when they're adding, they really mean to multiply them. So let's bring them together. The natural log of x plus 3 times x equals the natural log of 10. Now it's one natural log equal another natural log, so you're able to set their pieces together. X plus 3 times x equals 10. Let's multiply this out, distribute this out. So x squared plus 3x equals 10. Oh, x squared, we're going to be factoring in this problem. So you know with factoring, the principle that we use is zero factor property. So get a 0 over here. X squared plus 3x minus 10 equals 0. Now let's factor it. X and x. Signs need to be different. What two numbers multiply to give you 10 that are 3 apart from each other? That's 2 and 5. 5's the larger number. He needs to make his way to the plus sign. Now we got a 0. We factored it. Now use the property that allows you to set each piece equal to 0 and solve. So you're going to get a negative 5 and a positive 2. Let's check that out. If you plug in a negative 5, you're taking the natural log of negative 5 plus 3, which is the natural log of negative 2. Here you're committing another sin, natural log of -5. Can't do that. You can't have either one of them, certainly not both of them, being negatives. You can't take a natural log of a negative number. If you put a 2 in there, 2 plus 3 is 5, that's cool. Natural log of 2, that's cool. So this is a good answer for our problem. We only had one answer. Thought we were going to have 2, we ended up with just 1. Next page, number 5. The instructions say solve each equation, and it tells you above that logarithms only on one side of the equation. So we're looking at what to do if we have logs on just one side of the equation. You can see that on all of them we have logs on the left but not logs on the right, and the hint there, convert to exponential form. So we have got log of base 5, 3x plus 1 equals 2. It's in logarithmic form. Let's do that number to it. So 5 squared equals 3x plus 1. 5 squared is 25. Move the 1 over. And x equals 8. So we're getting an 8 for that. Let's just make sure that's legal. 3 times 8 is 24. 24 plus 1 is 25. That's a positive number, so we're good. And sure enough, what do you raise 5 to get 25? The answer to a log is always an exponent. 5 squared equals 25. So we're good there. It's a good answer. Let's see if I can fit a few more in here. We're doing 5A, B. Yeah, this was A. This is 5B. Let's see, B is underneath there. So 4 times the natural log of 3x equals 8. If we want to turn this into a logarithmic problem, or sorry, in an exponential, it is a logarithmic problem. We want to convert it to exponential form. We first want to get the natural log of 3x by itself. So divide both sides by 4, get the natural log of 3x equals 2. Now we're ready to do the circle around thing. You know that's a baby e right there. E is the base, raised to the second power equals 3x. Got that part. And then what we need to do next is we need to figure out what e squared is. So grab your calculator. There it is. So e key is right here. Second e key raised to the second power equals 7.389 and some change. That equals 3x. We are still trying to get x by itself, so divide both sides by 3. And x equals, take this number in your calculator and divide it by 3, and we're getting 2.4630. So 3 times 2.4360, if you took the natural log of that and multiplied times 4, you'd get 8. Let's see if we can't finish this one up on this, in this little area that we've got here, that I've got here. We're looking at, oh, we still got C and D. Okay, we'll do C. Log base 3 of x plus 6 minus log base 3 of x minus 2 equals 2. We're going to have to compact these. I mean, it's just begging to do it with a minus sign there. So log base 3 of x plus 6 over x minus 2 equals 2. There, now we've got a logarithmic equation. Let's do the circle thing. 3 squared equals that. 3 squared equals x plus 6 over x minus 2. You know that this is 9, so we've got 9 equals x plus 6 over x minus 2. I'm going to put that over 1 and cross multiply. So 9 times x minus 2 equals 1 times x plus 6. Let me take it up here. So we get 9x minus 18 equals x plus 6. Move the x over here. Add 18. 8x equals 24. So x equals 3. Let's make sure we can work that out. put a 3 in there. 3 plus 6 is 9. So this will be a 9. What do you raise 3 to make him be a 9? That's a 2. So let's put a 2 here. Minus, put in a 3 here. 3 minus 2 is 1. So we're getting a 1 out of that. What do you raise 3 to make him be a 1? You raise it to the 0 power. 2 minus 0 equals 2, so it just works all over the place. So x equals 3 for that answer of 5C. Okay, let's get started on another piece of paper. By the way, if you want 5 bonus points on your test, on test 4, you want 5 bonus points on your test 4, then text me the word green. Text me the word green to my phone, and I will give you 5 extra points on your test. And if you tell anybody about it, because I can see who has, oh, no big deal. I don't care if you tell anybody about it. Text me, because see, here's the deal. Nobody's watching Thomas's. You guys are going straight to mine. I get that. So text me the word green to my phone, and I'll give you some bonus points on the last test. If we take a last test. I don't even know how that's going to look right now. This is, what is today? When I'm recording this, today is the 29th, I think, of March. And I don't know what's going to happen with us. Okay, let's keep moving. We're looking at 5D. This is Thomas's 4.4 exponential and logarithmic equations. Everybody here's got an equation. It got an equal sign. So on this one we've got log, this is D, 5D, log of x, common log of x plus the common log of x minus 3 equals 1. How about if I move it up so you can see it? There you go. It's better than before. So I wrote it down. Now we want to make this into a logarithmic function, a logarithmic equation. You know, that's when we get to do the circle around. So this needs to be 1 log. It's got a plus sign between them, so you know that means that we're going to be multiplying x times x minus 3 equals 1. So we're ready to take 10, the understood 10 to the first equals that. Distribute here, so 10 equals x squared minus 3x. This is a quadratic, so we know the 10 wants to move over there. When he moves over, it becomes a minus 10. X plus and x minus, you know it's 2 times 5. 5 is a big number, he needs to land on the minus. So we get 0 equals x plus 2 and 0 equals x minus 5. So x is a 5 and x is a negative 2. Let's see which ones of those can last. Negative 2, you can't take any kind of log, natural or common, of a negative number. So that's gone. See if 5 will survive. Good, that's positive. 5 minus 3 is 2. That's good. So that's a good answer. 5 equals x. Okay, so we're done with number 5, and then we jump to number 16. Pretty sure Thomas, in all these A's, B's, C's, and D's, meant to number them separately. Don't know. Number 16. If $20,000 is invested in an account earning 2.5 interest compounded continuously, so you know you're using that PERT formula, determine how long it will take the money to grow to $45,000. So we have been given the accumulated amount, $45,000, and we're asked to find how long that money is going to have to sit in the bank. So let's use the formula. The accumulated amount, you want $45,000 out of that money. It began life, you put in the account $20,000. We'll multiply that times E raised to the rate, and the rate in this problem is 2.5%. Move it over 2 places. So we're multiplying times 0.25 times the time, times the number of years. We want to get E by itself, so let's divide both sides by 20,000. So we get E times 0.025 t. And actually, we know what E is. It's 2.71. We're trying to get t by itself. So t is our unknown. It's our variable. E is not a variable. It's a 2.71 and some change. So let's see. Let's grab this. Look at what we've got here. 45,000 divided by 20,000 equals 2.25. So we've got 2.25 happening at us. What we want to do now is we have got a situation where we want to slap natural logs on both of these. Let's turn it. We've got an exponential. There's an exponential. Variables in the exponent. So we're ready to slap natural logs, not common logs, because we're dealing with E. Natural log of E to the decimal point 0.025t. Okay, we're still working on getting t by itself. Let's go ahead and take care of this piece. Natural log of 2.25. Natural log of 2.25 equals, and I'm getting decimal point 810930216 equals, and there's more to it, it's just not written in my calculator, equals, let's send this piece to the front, so decimal point 0.025t times the natural log of E. This piece right here is one of our easy ones. It's one of our cute things we learned. What do you have to raise E to become E? This is like the natural log of E equals x. E to the x equals E. Well, it's going to have to be a 1. So this piece becomes a 1. We're multiplying times 1 there. So what we've got, it just sort of goes away. And now we're trying to solve for t. So divide by 0.025. I'm hoping you've left that number in your calculator. Divide it by 0.025. And we are getting t, the time, how long you've got to leave your money in there. We're getting 32.4 blah, blah, blah years. Rounded to the nearest year is going to be 32 years because that will drop off. So 32 years is what you need to do to leave your money in that account if you've got $20,000 and you want it to become $45,000. It's a long time. Let's move down here for our last problem in this section. Number 17 is talking about earthquakes. Log of E equals 5.24 plus 1.44 times big M. And big M has to be, this formula only works when the magnitude of the earthquake is over 5. Okay, the problem, I'm just reading it. The following formula relates the energy in joules released by an earthquake of magnitude M. What is the energy released by a magnitude 6 and a magnitude 7 earthquake? So let's look where M equals 6 and let's look where M equals 7 and see how those vary. And as a comparison, a 1 megaton nuclear weapon would have an energy release of 4.18 times 10 to the 15th joules, and the eruption of the volcano Krakatoa in 1883 produced an energy release of 2.09 times 10 to the 19th joules. I want to talk a little bit, teeny weeny bit, about what that times 10 to the means. Let's take the Krakatoa explosion. 2.09 times 10 to the 19th joules. That means move this decimal point 19 places to get the actual number. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 decimal point. And all those commas in there, I don't think it's worth it to show you how big that number, or to tell you how big that number is, but you get the idea. It's huge, that many joules of energy. So that Krakatoa at 2.09 times 10 to the 19th joules is the largest number that we're looking at in here, between the bomb and the two problems we're looking at. Okay, let's see what we've got. Log of E, meaning the number of joules that we can get out of this thing, equals 5.24 plus 1.44 times our 6 magnitude earthquake. So let's go ahead and do the math over here. Common log of E equals, let's do 1.44 times 6, and then add in 524. And we're getting 13.4 0.88. And now what we've got here is a logarithmic equation. Let's know that 10 is right there. Let's do our little circle. 10 to the 13.88 equals E. Okay, let's see what our calculator will tell us about that. Use this key if you want to, or 10 Humpy. I'm just going to use this one. 10 to the 13.88 equals, and that gives us E equals 7.59 if we're rounding to the hundredths place, times 10 to the 13th power. That's what that little 10 to the 13th out there is telling you. So to get this actual number, you'd have to take that decimal point and move it over 13 places, then put that decimal point there. You'd have this huge number. Let's see, times 10 to the 13. Let's look at what Thomas has given us. This is a 6 magnitude earthquake. An earthquake of magnitude 6 is still smaller than the 1 megaton nuclear weapon by about 100 places, by about 100 times. Let's look at if we jack it up to a 7 earthquake. Log of E equals 5.24 plus 144 times 7. Same game, 1.44 times 7, and then add in the 5.24. So we get equals 15.32. Log of E. We're going to do that thing next. Yeah, we are. We know that's an understood 10 in there. So 10 to the 15th, or 10 to the 15.32 is going to give us the energy out of that. Let's get your calculator going. Clear it. 10 to the 15.32 equals 2.09 times 10 to the 15th. Very close at least in terms of 2.09 to the Krakatoa, but this is 10 to the 4th difference. That's a 1 with 4 zeros. So Krakatoa was 10,000 times stronger than a magnitude 7 earthquake. This is raised to the 15th, and so is the nuclear weapon. So a magnitude 7 earthquake is about the equivalent of a 1 megaton nuclear weapon. So a lot of difference between a 6 and a 7. 10 to the 2nd difference, 100 times difference in the strength of a 6 magnitude earthquake and a 7. Okay, we're done.